Well, okay, let's go there. Unexplained variance. Not explained, right? Explained is good. Unexplained. What's another name for the unexplained variance?
Residual.
A residual is the precursor to it. Yeah. No, that's the good part. You guys are all looking in bold, like, what's the phrase there? Unexplained variance. You're getting there with the residual. It's that step right in between. It's a variance. Yeah. Yeah, variance of the estimate. Variance of the estimate. Or you could have said the standard error of the estimate. That would have been okay too. Right? But the variance of the estimate is a measure of how far those points are spread out around your regression line. That is also our unexplained variance. But since you brought it up, what is the coefficient of determination? The coefficient of determination. What does it tell me? And you're like, I have no friggin' clue this morning. Right? The coefficient of determination, what's the symbol for it? R squared. R squared. Okay, good. We're getting close to our correlation coefficient, yeah? So it tells me the amount, or the proportion of the variability, or the variance, explained or accounted for or predicted by my x variable. If you're regressing y on x. You're using x to predict y. Okay? So the coefficient of determination is that r squared, that proportion of variability that's explained. Okay. Okay, good. Any questions from that we talked about? Because we're just finishing up today. That was just kind of the brief review on regression. Okay, good. So where are we finishing up? Okay. So the good news for today is, well, oh, actually, what was that thing I wanted to get back to? And I said I was going to get back to it. It's gone. It's gone. All right. Probably wasn't important. It won't be tested anyway. Okay. Yeah, do you remember?
Yeah, you said best fitting.
Thank you. Good, best fitting. Okay, so best fitting, when we talk about best fitting, it's essentially, it's like a least squares estimate. That line, meaning what? The error around it is the smallest around that line than any other line. Right? Just like a variance or a standard deviation gives you the smallest amount of variability around the mean. So the regression line using these equations gives us the least amount of variability around that line than the amount of variability you would get around any other line you put through that data. Do I need to repeat that? Say that again? Okay. Get the picture in your head, right? We put a line through this data using these particular equations for slope and intercept. Those equations give us the line that gives us the least amount of error around it. Right? Because if I have a scatter plot, I could put lines anyway through it, right? Like, what determines how I put the line through that data? Well, you want the line through the data that gives you the smallest amount of error, the smallest amount of variability. That's the line that we're using, this equation. This regression equation, the equations for the slope and the intercepts, that's what this gives us. It's the best fitting line. Okay? Thank you for remembering that. Now, we also learned last week, if somebody gives you an x variable, then, an x value, how to predict y. Right? How do we do it? We just took our x, put it in the equation, and crunched the numbers and got a predicted y. That was a point estimate. Right? Just like when we use the mean. It's a point estimate. It's one value. So what I could do is, instead of a point estimate, what have we been doing all semester? Interval estimates, right? Interval estimates. I could create a confidence interval around a prediction, so that my prediction is not just one value, but a range of values. Okay? So let's take a look at this for a minute. What is our normal way to create a confidence interval? We start with a point estimate in the middle, plus or minus a certain amount, right? This has been all semester. What's the certain amount? A critical value times some type of standard error, right? What do we have here? Well, y prime, that's my predicted y, that's my point estimate, plus or minus a critical value times a standard error. What is this? Okay, this. This, we call it a correction factor. We call it a correction factor because this bit alone is not enough for my confidence interval. It's really not, because there are two sources of error that go into this prediction. So this component corrects for it. So what are my two sources of error? One source of error is that our correlation is not perfect, right? As long as my correlation is less than 1, positive 1 or negative 1, it's not a perfect correlation. Okay? So that means there's some error, there's some uncertainty associated with the prediction. The second source of error is every time I take a different sample, right, from the same population, I'm doing the same thing, but every time I take a sample, I'm going to get a slightly different line, right? My regression equation is going to be slightly different every time I take a different sample. So that's also a source of error. So those two sources of error lead us to need this correction factor. Okay? Now you want your good news for Monday morning? I'm not going to ask you to calculate this. You don't need to know confidence intervals. I just wanted to talk about it in broad context. Now that you've finally gotten it down, right? I just wanted to talk to you about it in broad context, that you could do this kind of prediction, a range, an interval prediction, rather than in a point estimate. And you could do that, but you would need this correction factor because of our two sources of error. Those are the main things I want you to get. And the bottom line here, remember something. Unless your correlation is high, there's a lot of room for error. We make predictions. Like, this is what I want you to understand as consumers of knowledge, right? When people are making predictions based on these numbers, there is error involved. It is probabilistic. It's not like here is the answer with a capital T and a capital A. You should just understand that, especially as the correlation gets weaker. Okay. Now, because we've always been learning these things, we have to talk about our assumptions. Let's talk about our assumptions, okay? And again, this is when I'm generalizing to a population. So, first assumption, independent random sampling. Again, what am I talking about is independent here? Which things should be independent? My x variable and my y variable? What's going to be independent? Yeah. Well, in theory, like a sample might be independent, but within one sample, what's going to be independent? Each pair of scores has to be independent of the others. Right? Like if you're doing height and weight and you get the height and weight of a husband, you're not necessarily going to want to get that for the wife as well. Okay? Because there's a relationship there that will interfere. No. Like across pairs, right? Like if you're doing height and weight, the height and the weight are not going to be independent because a person is going to give you both values. They're related because it comes from the same person, right? But if you give me height and weight, and you give me height and weight, and you give me height and weight, in theory, those might be independent. Yeah, in this class, it might be independent. In some other setting, you might think not. Within one class, you might have questions, although I doubt that would be an issue. But right, that's what should be independent. Okay? Linearity, as we talked about with correlation, right? The underlying data structure must be linear. That is, you can put a straight line through it. If it's curvilinear or some other shape, then it's not going to be explained well by this kind of regression line. You would just pick some other kind of analysis. We're not going to talk about it because it's beyond the scope of a basic stats class, but you have to find another instrument. Okay? So that's linearity. What about normal distributions? Now, let me just show you. We talk about having our variables normally distributed, but this is an additional thing. What this means, let's look back at this scatter plot for a minute. When we talk about normal distributions, what it means is for every x value, right? Every x value, the y-scores should be normally distributed. Okay? For every x, the y-values should be normally distributed. That's an important assumption as well. And then the last assumption here is a good word, homoskedasticity. This is why you're paying a lot of money for education. So you can say words like homoskedasticity. Homoskedasticity, even though it sounds intimidating, is essentially homogeneity of variance for your regression line. That is, watch. Just your basic scatter plot. Okay? And I put a line through it. Not such a good line, but let's add some points there. Okay? I put a straight line through it, right? And I talked about the measures of variability we use, right? Variance of the estimate, standard error of the estimate, right? The variance of the estimate is one number reflecting the variability of these points around the line. It's one number. You can only use that one number if, in fact, you have approximately the same variability anywhere around the line. Homoskedasticity. The variability has to be the same around the line at all the different points. An example where that would not be the case is if you got something that looks something like this. Okay? Look at this one for a minute. The variability at the lower x values is much different from the variability at the higher x values. So in that second case, you don't have homoskedasticity, in which case the variance of the estimate would not be a good measure of variability, right? Because it's like you're averaging the variability, but it's not the same all over the place. Okay, so it's just like homogeneity of variance. All right, questions on that? Okay, good. Now we talk about when to use linear regression. This is actually used a lot. It really depends on the discipline that you're in. Like economics uses regression a lot. Different areas of psychology, like social psychology, might use regression a lot more than other things. It's a very, very useful tool. First of all, prediction. I have a couple things to talk about with prediction. One, an article by the guys who wrote the book Freakonomics, actually. And they were talking about rainfall. How does rainfall affect various things, right? Because, we can talk about how rainfall affects like crops and stuff like that, but it has wider ranging effects. So they looked at a paper about 19th century Bavaria, okay? 19th century Bavaria, where they kept very good records. And in 19th century Bavaria, there was excessive rain that damaged the rye crop, okay, by interfering with planting and harvest, okay? So it damaged the rye crop. So what happens? Well, they found that food prices went up. Okay, totally makes sense. Rye was a big part of their diet. This is not a big surprise. But when they looked at other things, because again, we're not just talking about how rainfall might affect crops. That's obvious. What about other things like crime? Okay? They found a startlingly robust correlation between the amount of rain, the price of rye, and the rate of property crime. Okay. Does that make sense to you? Why? I'm seeing you nod. Why? Why does that make sense? Yeah. No. The rye crop was being destroyed. Oh. The rye crop was being destroyed by too much rain. So food prices went up and property crime went up.
There wouldn't be enough to go around, so people would start stealing.
Yeah. At least in theory, right? So people started stealing. However, one of the interesting things was violent crime fell during the rainy years. So property crime went up, violent crime fell. Any thoughts why that might be? And again, you have to be careful when you're talking about causality, all right? But this is looking at correlations and predictions. Yeah?
Maybe if people are hungry, they're less likely to commit a violent crime because they don't have enough energy.
Unfortunately, maybe that would be nice, but no, we seem to find the energy to commit violent crimes even when we're hungry. But it's a good explanation. Anything else? There's a particular word that I've used that would clue you in. What was destroyed? What did I say was destroyed? Which crop? Yeah. Any clues? Yeah.
Make it alcohol.
Yeah.
Drinking less.
Yeah. They were drinking less because rye goes into beer, and they had a really high rate of consumption of beer, so that dropped as well. Okay? So it's not just, okay, rain affects crops. It's like, what else does it affect? All right? Another thing, but right there is this relationship between rain and violent crime. Okay? And they looked at sub-Saharan Africa. And yeah, this was very sad. 29 of 43 countries in sub-Saharan Africa experienced some kind of civil war during the 80s and 90s. The causes of any war are, of course, incredibly complex, but economists discovered that one of the most reliable predictors of civil war is lack of rain. Again, it's not saying that lack of rain directly causes civil war, but you can use it, and this is a case where it's like nice to understand, you might be able to use it as a predictor, right? Why? Because when there's a lack of rain, economic downturn. Economic downturn, economic unrest very often leads to civil unrest. Okay? So this is a case where you use regression for things like that. Here's something that's more important to you personally. SAT scores. How many of you think that your SAT scores were a good predictor of how you were going to do in college? This is the typical response I get. Okay, what about your high school GPA? Do you think that that's a reasonable predictor for some of you more than others? Yeah, the rest of you are like, yeah, no, they had no idea who I was. This is totally, right? Okay, so here's an interesting thing, right? They use SAT scores and GPA as predictors of how you're going to do in college. That's why they use it as, an admissions criteria, right? Why would they use it? But so listen, okay? SAT alone, let's look at the correlation between SAT alone and your freshman GPA. What is that? So the correlation between your SAT scores and your freshman GPA, and by the way, these are ETS numbers from a couple of years ago, so I'm not sure exactly how valid they are now, but they should be close. The correlation is 0.52. That's not bad, eh? But it's still, if we turn that into R squared, right? What's R squared? Right? First of all, it's 0.27. So that means, again, 27% of your freshman college GPA variability can be explained by your SAT scores. 27% doesn't sound like a lot, does it? Right? So even though the correlation is high, it's still only explaining part of your performance. All right, what about GPA? GPA alone, the correlation's a little higher, 0.54. So its R squared, its coefficient of determination, is 0.29. Okay? 29% of the variability. Woohoo! Okay? What if we put them together? Together, because again, that's multiple regression, which we're not going to do, but you could do that. Together, high school GPA and SAT correlate with freshman GPA with 0.61. So that is an R squared of 0.37. 37% of the variability of your performance could be predicted by GPA and high school grades together, SAT scores together. Okay? So understand something, right? But why do we use this? It doesn't sound like a lot. But you know what? It's probably still the best predictor we have, especially if you're talking about cost efficiency, right? Like, you know, if you want to say, well, really, I have a portfolio of work, and if I had ongoing conversations and interviews with these people, they would understand how much, you know, I have to offer to a particular school, and then they could really estimate how well I'm going to do in college. It's not going to happen, right? Because there's thousands and thousands of applicants. So if they're just looking for one-shot numbers to make predictions, actually 37% of the variability is a big chunk. Okay? So you should just understand this is where this stuff comes from. Even if you never do it, you should have some understanding of where these things come from because it's useful, you know? Okay. So that's prediction, right? What's the other things we use for? Statistical control. Here's an interesting thing. What if I wanted to predict hoop shooting ability from somebody's numbers of years of basketball training? Okay? I want to see if training will predict how many hoops a person shoots, you know, how many shots they actually make. Okay? Now, can you think of a variable that could confound that problem? A pretty obvious one. Yeah? The height, you said the height of the hoop. That's interesting. That's not what I was thinking of. The height of what? The people. The people, right? Because in theory, you leave the height the same. But the height of the people, right? Like, no matter how many years of training in basketball I might have, you know, I'm still not going to compete real well against somebody who's 6'5". It's just not going to happen. So what you can do in regression is you can predict a person's ability from, let's say, their height, and then subtract that out. So all you're left with is their training and their ability. It's a way of partialing out effects. And it's a very useful thing. Again, it's not, you know, we're not getting into this because we're doing the simple version, but you should know those tools are out there if you want to get rid of one possible confounding factor or others to make your predictions. Okay? And then regression with manipulated variables. We don't talk about this a lot, but if you've noticed, the examples I've been talking about, the variables are not what we call manipulated. Manipulated meaning under researcher control, right? When we talked about children's ages, or if you talk about anxiety scores, or any of those things to use to predict another thing, GPA and SAT scores, right? They're not under a researcher's ability to control. They're not manipulated. Sometimes you can do a manipulated variable. For example, if I wanted to use, and this also applies to you, the number of hours of sleep deprivation and how people do on exams, right? Well, how would I really do it? If I was serious about doing this, I'd have to set up groups of people, have a sleep lab, and determine, okay, you guys get no sleep deprivation, you guys get 8 hours of sleep deprivation, you guys get 16 hours of sleep deprivation, and set it up like that, and then see how well they do. Then I could use regression to predict from the hours of sleep deprivation. But that is a manipulated variable. Okay? So it's possible, but not as common. All right? I think that's it for regression. Anybody have any questions or comments? Oh, but you know what we're going to do? We're going to do one more example. That's what we're going to do. Let's do one more regression example. And then, so we're just going to put into play all the pieces of information we have. 8, 9, 7, 4. Oh, I inverted these numbers. Sorry. 8, 9, 7, 4. Weird harmonics of this place. Okay? All right, so we're using an anxiety rating of some kind on a scale from like 0 to 10 to predict how people do in exam scores on their exams. Okay? Oh, and one other piece of information I should give you that will make life infinitely easier is that. Okay? What kind of correlation is it? Yeah, negative meaning what? For this example, by the way, when I ask you on an exam what this means, I want it specific to the example. Okay? It needs to be. If everybody just gives me the definition of what a negative correlation is, I'm not impressed. I want to know for this study. So what do we mean here? It's very simple. Yeah, as anxiety is increasing, the scores are decreasing, which you might expect. Okay? And what size is that correlation?
Large.
Yeah, it's a large correlation, a very large correlation. All right, let's get the equation of the line. First, we get the slope. By the way, remember also the slope is going to have the same sign as the correlation coefficient. That's a way also to make sure you're not dropping negative signs somewhere. Right? Because think about it. The slope, the slope indicates the direction that the line is going in. And so that's how your scatter plot is going to be also. So the correlation and the slope always have the same direction. Okay? Now let's get our intercept. Yeah, just be careful with your negative signs. That's the only time I see people making mistakes on regression. Really. So my line is that's the equation for my regression line. Okay. So now, if somebody walks in and I say, okay, here, you have to take this anxiety test, and they get an anxiety score of 3, what would I predict for their test score? Or how would I do it?
Put the anxiety score in as X.
Yeah, just plug it in. Okay. Now, if I wanted to know the proportion of the variability explained by anxiety, how do I find it? The proportion of the variability in the exam scores that's explained by their anxiety levels. How do I do it? That's R squared, yeah. Okay, so what do we say then? We say that, well, 79.03% of the variability in their exam scores is explained by the variability in their anxiety scores, their anxiety ratings. Which is actually a really large amount if you stop and think about it. So how much is not explained? What's the notation for that? K squared, right? How do I get K squared? Yeah. Okay. But now let's say I wanted it in numbers. So let's say I want the variance of the estimate. So the variance of the estimate, and again, this is a sample, okay? This is a sample, so you're using the variance of the estimate formula here, the sample formula. What was n? It was 6. Did I give you the variance of the y-scores, by the way? What did I give you? I gave you the standard deviation of those y-scores, so you have to remember to square it. Okay. By the way, what's another name for the variance of the y-scores? Anybody remember the variance of the y-scores? Another name for it. No. No. Like literally just another name for it. Yeah.
The residual?
Now, remember what a residual is. A residual is the difference between your actual score and your predicted score. Remember, we had explained variance. We had unexplained variance. What did those add up to? Total variance. Total variance is the variance of the y-scores. The variance of the y-scores. See, it's really useful to keep going back and trying to connect those dots, because otherwise it just becomes these like disembodied pieces of information. Okay? Now, if I was going to test this for, if I was going to test the correlation coefficient for significance, all right? First of all, does anybody remember what would the hypothesis be? What would the null hypothesis be if I wanted to test the correlation coefficient for significance? Yeah.
That anxiety has no effect on test scores?
okay, in words, yeah, that there's no relationship. Don't say has no effect because it sounds too causality related, but there's no relationship. Okay? How do I write it in symbols? What do you do in symbols here? I'm talking about the correlation coefficient. Anybody remember? What's the population correlation coefficient? Okay. How about rho? And you guys are like, oh yeah, I remember that. Yeah, rho is equal to 0. Okay? So the correlation, right, and that's the population correlation coefficient is equal to 0. So how would I test this for significance? What would I do? What's the big thing that I would do to test this correlation of minus 0.889 for significance? It's very complicated. What do I have to do? Okay, any guesses? Anybody awake out there this morning? Yes, thank you.
You match it to a critical T using the degrees of freedom, which is n-2.
Almost. I'm going to match it to a critical value of R, right? We had a whole table of R critical values. R critical values. We don't have to do any more calculation. It's done for us, right? So our critical value. But as you mentioned, with degrees of freedom of n minus 2, so it's 4 degrees of freedom. So the R critical value, you can check it out yourselves. I'm just going to give it to you. Is 0.81. So therefore what? What's my conclusion here? What's my conclusion? Do I reject or do I fail to reject? I reject, meaning what? Yeah, there's a relationship between anxiety and these exam scores. Okay? Yeah?
So what are you comparing to the R critical value?
The R that we have, the R obtained, right? So that was the minus 0.889, I think it was. Yeah. Yeah.
So then for the alternative hypothesis, would you just put rho is not equal to 0?
Yeah. Yeah. Okay, any questions on this? Yeah.
How do you round, like, for the degrees of freedom where it's like, especially at the bottom, like it goes from like 120 to 150 and then
So when,
it's in the middle.
yeah. What's the rule?
Go down.
Go down. Okay. I made it an easy rule. If you were doing it somewhere else, it might be different, but that's our rule. Okay, now I think we're done with regression, unless anybody has another question. Yeah?
Can you just explain K squared?
Okay, so do you get what R squared is? Okay, so R squared is how much of the variability is explained by anxiety. K squared is how much is not. Right? So that stuff that's not explained, well, what is that explained by? Individual differences, testing conditions. There's all sorts of extraneous error that we don't know what it's due to, right? That's what that is. That's what K squared is.
Why do you square R squared?
No. K squared is 1 minus R squared.
Oh, okay. That's what I thought, and then there's like a...
Well, because what I did was I just stuck in the 1 minus R squared. I just stuck it in there. You see it in that one?
Yeah.
And K squared is just 1 minus that R squared. Okay, good? Yes?
So what will we have to really like be able to generate as far as numbers for regression? The unexplained variance and explained, like just what we did in the example?
Everything that I've talked about.
So, but I mean, like, what is the...
No, I mean, we've done everything.
Right.
We've done everything.
Okay.
Yeah. Yeah, if you can do these examples and the examples in lab, like this is it, you know? This is all the numbers that we're talking about. Okay? What's the unexplained variance? The unexplained variance is the variance of the estimate. Right? So that's the same thing. Okay? Now are we done? Okay, good. All right. Well, we are going to do chapter 11. We're going to start it anyway. And chapter 11 is very easy. Even easier than correlation and regression. Because chapter 11, yeah, stretch for a minute, breathe. Chapter 11 takes us back to t-scores, t-tests. Okay? Now, when we did t-tests before, for two groups, we're still talking about two groups. When we did t-tests for two groups before, our groups were not related to each other. They were independent. So we had t-tests for independent groups, right? That's what we did. And we learned all those formulas, and we had the flow chart, and that was done. Now we're going to talk about what if your sets of scores are related to each other in some ways, if they're dependent. Then what can you do? Okay? And it's actually going to be easier and in some ways more beneficial. So let's take a look at this example and we'll talk about it. All right? So in this example, I wanted to study whether hypnosis has an effect on the number of cigarettes people smoke. Okay? So this is a study. So I ask people on a given day, what's the average number of cigarettes they smoke? Then I put them under hypnosis, and I give them some kind of hypnotic suggestion like, every time you light up, you're going to feel nauseous, or something like that. And then after, let's say, a week, I measure the number of cigarettes that they're smoking. Okay? This is a very simple version of something called a before-after design. You measure them before, you do something, you measure them after. A before-after design. Okay? Now, let's look at the means down here. 27.2 cigarettes before, 21.8 after. So maybe that's a decrease, but we don't know. So what would we normally do to see if those are significantly different from each other? What would we do? You know how to do this. A t-test, good. What kind of t-test? Which one? Are the samples large? No. Are they equal? Yes. Equal sample sizes, yes. There's 5 scores before and 5 after. Yeah, so we would do a t-test for equal sample sizes. Let's just do that really quickly. I'm just going to jot it down because I want you to see what happens. This is not how you would normally do it. This will be useful for us to look at. What is n here? Just to remind you. 5, good. What do you think? Significant or not? Folks, it's less than 1. Not likely, not likely. What would you normally do to find significance? You get your critical T with how many degrees of freedom, by the way, would you need? What would the degrees of freedom be for this? 8, right? N1 plus N2 minus 2. Or you think you take a degree of freedom off from each group. Right? And I would look up the T critical value. I don't actually happen to have that number with me. If anybody wants to look it up and let me know, I'll put it up here. I don't feel like looking it up now. But we know that 0.99 is not significant. Essentially what you're saying is the difference between the means is approximately equal to the amount of variability that's going on. Okay? So there's no way to tell if those groups are actually different from each other because there's so much variability. Again, this is an example of what we call noisy data. It's obscuring any possible difference. Okay? Now, Why is that? What's the problem here? Well, let's take a look. We can look at numbers, and we're going to look at the graph on the next page, because there's a better way to analyze this. All right? Let's just look at the numbers. Let's look at these before numbers. Notice something. There's a lot of variability among the people in the number of cigarettes they've smoked before. Right? You're just looking at the number of cigarettes smoked before. That's this column. Right? Number 1 is only doing 19 cigarettes a day, but number 2 is doing 35 cigarettes a day. That's a lot of variability. That's a lot of variability. So there's so much variability here that that's increasing that denominator and making it hard for us to see if there's a difference. But let's look at the next page. Let's look at the graph, because something interesting is going on. With the exception of one person, what's happening? Mostly, people are smoking fewer cigarettes after hypnosis. With the exception of one person, they're all smoking fewer cigarettes after hypnosis. That's a pattern that we want to find, right? Because it's there. They mostly smoked fewer cigarettes. How do I find that difference? Well, I have to get rid of all the variability that comes just from, we were talking about before, individual differences, right? Number 2 is smoking 35 cigarettes. Number 1 is only smoking 19 cigarettes. There's a lot of individual variability, individual differences. So we would like to get rid of that so we can just find out how much of the variance is due to whether hypnosis is working or not. So what we're going to do is we're going to analyze this in a slightly different way, but simpler than you've actually done. So it's not going to be difficult. We're going to use something called, he calls it the direct difference method. I've never actually seen that term used, but it's fine. It's a way of doing a t-test that takes into account that these two sets of scores are related to each other. Right? They're related to each other. Why are the before and after scores related to each other? It's the same person giving you both scores. Which is why, by the way, we do correlation before we do this chapter. There's a relationship there. Okay? So the direct difference method is very simple. What do? We take these two sets of scores, and instead of looking at them as two sets of scores, we treat them as one set of different scores. So let's take a look at the next page. Okay, this is what we do. Look down here. We have our before scores, we have our after scores. D means the difference scores. How do I get my difference scores? I subtract. 19 minus 12 equals 7. 35 minus 36 equals minus 1. Those are my difference scores. They're just difference scores. But then what I'm left with is one set of difference scores. How do I analyze one set of scores? I do a one sample t-test. And one sample t-test was easier than two samples even. So that's what we're going to do. Okay? Now, what's the hypothesis that we're testing? When we're using this direct difference method, when our two sets of scores are related to each other, this is the hypothesis we generally use. What is mu sub d? The population mean of the difference scores. The population mean of the difference scores. So if I say the population mean of the difference scores is equal to 0, what am I saying? There's no difference. There's no difference between these groups. The alternative would be it's not equal to 0. And again, this is how I set this up is a non-directional hypothesis. Right? It's a non-directional hypothesis. You could set it up as a directional hypothesis, that it will definitely it'll definitely decrease the number of cigarettes they smoke or something like that, in which case you'd write it differently. But we have this non-directional hypothesis. Okay? So that's what we're testing. Here's my t-test. This is just like, right? This was when I had one sample, right? Or you could have written it like this. right? This is the same thing. It's the same thing. Here, we have d bar on top. What's d bar? The sample mean of our difference scores. The sample mean of our difference scores. Why did mu fall out? Can anybody see why did that mu fall out over here? Why do I not have it here? Yeah. Yeah, I'm hypothesizing that mu d is 0, so we don't even include it. We don't even include it. And then I'm dividing by this. What is this? This component in the bottom? SD bar. That's the standard error of the difference scores. The standard error of the difference scores. This is nothing different from anything you've seen before, except instead of x, now we're using d. Just to remind ourselves that they're difference scores. Okay? So what do we need to get? Well, we need to get the mean of the difference scores. How do I get the mean of the difference scores? I add up all the difference scores and divide by n. What is n going to be? What's n going to be? Yeah, it's going to be 5, right? It's the number of pairs of scores. The number of pairs of scores. And I need to get the standard deviation of my difference scores. Let's actually do that. Even though I give it to you, let's see it. What you could surely do is take any standard deviation formula and just stick the difference scores instead of x. You could do that. But here's the formula that he puts out in the book. He just substitutes it for you. That's the standard deviation of the difference scores. So yes, our n is 5. Our sum of d squared, right? I had to take my difference scores, square them, and if I added those up, those gives me the sum of d squared. Oh my God, it's turning purple. How long has it been purple? A while. Can you guys see? They told me the cord is wonky. Was it having a calming effect, or was it psychedelic? I tell you, between I have these odd harmonics. It's like a sitar going in the back. I don't know if you guys can hear it. It's like a sitar going in the back, and that's turning purple. If there starts to be a strobe light, we're done. We're just done. Okay. So that's my standard deviation of my difference scores. So now if I want to do the t-test, just get straight. The thing you need to get straight here, or you need to remember, is what is S sub d and what is S sub d bar? Right? S sub d is the standard deviation of the difference scores. S sub d bar is the standard error. Okay? And the standard error is always the denominator of your t-test. Notice something? The numerator didn't change from the t-test we did on top, right? The difference between the two sets of scores is the same. It doesn't matter whether you look at the difference between two means or if you look at the mean of the difference scores. They're the same thing. Sometimes it's useful to actually calculate the means of the groups and then subtract them to make sure you did it right. So what do we have here? Okay. So the numerators of those t-tests are exactly the same. So what's different? The denominators, right? The denominators between up there was 5.45, down here is 1.5997. Okay, that 1.5997, that's the standard error of your difference scores. Okay, what happened? How did this get so much smaller? What we've done, what this direct difference method does, is it subtracts out the variance that's due to all these individual difference scores, all these individual differences, all that error that doesn't apply to the actual study that's going on. So the denominator is smaller, and if your denominator is smaller, right, your standard error is smaller, what happens to your t-score? Gets bigger, right? As your standard error goes down, your t goes up. So if I wanted to test this for significance now, what do? I still have to get a t-critical value, right? But what are my degrees of freedom? Anyone want to take a guess? Yeah, go ahead. You're right. You are right. The degrees of freedom are n minus 1. Because, again, I've turned it into one group of difference scores. So I have 5 different scores. It's like a one-sample test. So my degrees of freedom are 4. So if this is the case, my t-critical value is 2.776. What's my conclusion here? Do I reject or do I fail to reject? Yeah, I reject, right? And I say, yes, hypnosis made a difference. Couldn't do that before, right? Wasn't significant before. Significant now. Because I took all sorts of variability that was useless to this, that was obscuring the pattern, and I got rid of it. I'm only able to do that because the two sets of scores are related to each other. And they're related to each other. When I say they're related to each other, what does that mean? There's a correlation between the two sets of scores. Now, why does it make sense that there's a correlation between those two sets of scores? Because it's the same person giving you two pieces of information. All right? Whenever somebody gives you two pieces of information from themselves, they're related. Right? Another way of saying that is that they're dependent, right? They're not, if you say that things are independent, they're not related in any way. So these are dependent. Dependent, which is, by the way, another name for this test. People will call it a dependent t-test, a correlated t-test, a matched t-test. All right? All those words mean that there's a relationship going there. I mean, here's an interesting little thing, right? I was doing vision research, and we were studying glasses. And so we would test people. We'd get a variety of different measures. And the people I was working with kept telling me, we were measuring right and left eyes. And they said, well, you have the right eyes and the left eyes. Let's treat them as if they're independent. And then you can have twice as many eyes being measured. I said, but they come from the same people. They're related. Like, no, they're not related, even though it's the same. They're two eyes from the same person. So, because what they were more interested in was increasing their sample size rather than looking at the differences between the two sets of eyes. There's no reason to believe that, your two eyes are not related in some way to each other, at least not as far as I can tell. Okay? So those are the basics of how to do this test. You see, it's real simple. But let's talk a little bit more about why it works. All right, the matched t-test is a function of linear correlation. Look what's going on here. The degree to which the matched t is larger, right? So this is a matched t-test. For the same data, depends on how highly correlated. Okay, look at this formula. This formula is another way to do the same t-test we did. You're not going to use this formula. You're not going to use this formula for any calculations. It's more to show you what's going on. So what's going on? If I took away this, what is that? That's just your regular t-test that we did in the first place, right? This is a component, it's variance, that we can subtract out based on correlation, based on how related the two groups are. Okay? If my correlation is 0, I'm left with your regular good old t-test. If it's not, then I get to reduce this denominator. I make it smaller. The larger your correlation, the more you get to reduce that denominator. So this is like this is just a clearer explanation of what we just did in the direct difference method. The direct difference method is just an easy computational way of doing it. This is exactly what's going on, though. All right? So as your correlation gets more positive, you get a smaller denominator and a larger t. That makes sense. We've talked about that a lot. If your correlation was negative, then you'd actually be making the denominator bigger. But you would never do that. Like, you would never set up an analysis with a negative correlation like that. What you might do is you might flip around a variable. For example, let's say you're looking at the number of hours people study and the number of errors they make on a test. So that's a negative correlation, right? As one is going up, the other is hopefully going down. So what you might do is you might flip around that variable. Instead of looking at the number of errors they make, look at the number of answers they get correct. Then what you have is a positive correlation for the same data, right? You've just altered how you look at it. And then you could do this. Okay? All things being equal, as R increases, so does T. That's a nice thing. Now, here's a little thing to show you. If I increase R, I actually decrease the variability of the difference scores. How does that work? Imagine I have two sets of scores here, okay? 30, 40, 50. That's one set of scores. The other set of scores I'm going to get by adding 10. Okay? What's the correlation between those two sets of scores? It's perfect, right? Because what did I do here? Just by adding 10, what is that called? Yeah. Yeah, it's a linear transformation. Good, right? A linear transformation, I just added 10. So if one variable is a linear transform of the other variable, it's a perfect correlation. Okay, good. What are my difference scores? What are the difference scores there? Yeah, they're all 10, right? What's the variability of my difference scores? 0, right? There's no variability. There's no variability. As your correlation increases, the variability of the difference scores decreases. Okay? Which is good. All right. So we have that. Okay. So that term, right, in that formula, that second term in the denominator that's being subtracted, we talk about that as extraneous variance. It's variance we don't need, right? It's the variance that the matched scores share. When you get rid of that extraneous variance, what you're left with is treatment variance, variance that's due to hypnosis, or whatever it is that you're looking at. This variance, that treatment variance, is completely unrelated to the fact that subjects differ in the amount of cigarettes smoked at the beginning of the experiment. Okay? That's what you want to get rid of. You want to get rid of the individual differences so that what you're left with is variability due to whatever your treatment is. That's what you want to understand. Okay? So, what is our only disadvantage? Why are we not trying to do this all the time? The disadvantage of the matched T is degrees of freedom. How many degrees of freedom did we have the first time around when we did this? When we did this, the independent T for this study? 8. How many with the matched T? 4. We have half as many degrees of freedom. If you have fewer degrees of freedom, what happens to your T critical value? It gets bigger. If your critical value is bigger, that means it's harder to reject, right? So that's the drawback here, is we get a larger T observed, but we also get a larger T critical value. Usually, that still works in our favor. Usually, that still works in our favor. Because the denominator, what you get when the smaller denominator usually makes it worth your while. Unless your N is very low and your R is low. You have a small sample size and a small correlation, then it may not be worth it. Then it may not be worth it. Okay? We don't very often do match designs with large samples. That's not so typical. And just to talk about this particular design, we're going to end up here, is what's the problem with the before-after design? Basically, you have no control group. You have no control group. You know, if I took a bunch of depressives and I measure their depression before, give them a drug, and then measure their depression afterwards, how do I know if the reduction in depression is due to the drug? In the hypnosis example, how do I know that the reduction in cigarettes is due to hypnosis? How do I know? You don't. You don't. So you need a control group when you're doing this. Sometimes you need more than one control group, actually. So you have to be careful. Like if you're thinking about designing any studies or whatever, just be really careful with this kind of stuff because it's really appealing. It's a really appealing design. I look at them now, I do something, and I look at them afterwards. But there's a lot of room for making mistakes. Okay? So let's end there, and we'll pick this up on Wednesday.